Modeling human driver is challenging because of the uncertainty in human behavior and complex interactions among drivers. Recently, black box models like deep learning-based models have gained much attention. These models are highly expressive so that they can learn complex behaviors from data. However, they lack interpretability of the underlying dynamics. On the other hand, white box models or rule-based models are often governed by a small set of predefined parameters. These models are more interpretable and simple, which makes it easier to prevent unacceptable behavior. However, they cannot model the inherent stochasticity of human behavior. In order to mitigate the limitations of both models, we developed a gray box model where the parameters of the rule-based models are learned in a data-driven way. The driver behavior can be decomposed into two components: the longitudinal motion along the lane and the lateral motion, including lane-changing behavior. For the rule-based models, we use the stochastic IDM to model the longitudinal motion, and mobile, which will be introduced in the next slides, for the lane-changing behavior. The standard IDM, or intelligent driver model, determines the longitudinal accelerations so that the vehicle can drive at its desired speed while maintaining the safe separation from the vehicle in front. The stochastic IDM is an extension of standard IDM, which has an additional variance term. Mobile determines whether to initiate a lane change in order to maximize the longitudinal accelerations of the ego vehicle and its neighbors, defined as the old follower and the new follower. Here, the longitudinal accelerations of the ego vehicle and its neighbors are computed using the stochastic IDM. Based on these driver models, we developed a method to learn the probability distribution over the parameters of these rule-based models using real-world data. In this work, X denotes a set of known variables, which are the longitudinal and lateral position measurements of each vehicle. Then Z denotes a set of latent variables, including the desired longitudinal speed and the variance term from the stochastic IDM, the politeness term from the mobile, and a lane-changing parameter, lambda. Given the latent variables, we can compute F lane, the probability of the ith vehicle changing lane. Here, we changed the hard constraint of mobile into a soft one using a sigmoid function. Lambda governs the degree of preference for changing lanes. The empirical likelihood of the next observation, X dash, can be obtained from the weighted sum of two cases, the lane changing case and the lane following case. Our goal is to find data that maximizes the empirical log likelihood of all the observations. Theta is a set of parameters that govern the distributions over the latent variables Z for each vehicle. In this work, we assumed that each variable follows a multinomial distribution. To estimate the parameters, we use the expectation maximization algorithm. In the E step, the posterior probabilities of Z given X and theta are computed. And in the M step, the maximum likelihood estimate for theta is computed. These two steps are iterated until convergence. For experiments, we used a real-world data set called interaction. And we used two baseline models to compare our model against. The first one uses the default IDM and mobile parameter values fixed for all vehicles. And the second model uses particle filtering to estimate the distributions over the latent variables. We evaluated the models in terms of prediction accuracy, data efficiency, and safety. The prediction accuracy is measured using the average displacement error and the final displacement error between the simulated trajectories and the ground truth trajectories. The data efficiency is evaluated by training the models with subsets of data set with different sizes and measuring their accuracy performance. And the safety is evaluated by counting the frequency of undesirable behaviors in the simulated trajectories, including conclusions and heartbreaks. Results show that our model outperforms the default model and shows nearly equivalent performance to the particle filtering-based model with less amount of data. To summarize, we developed a gray box model to achieve both interpretability and variability. We estimated distributions over IDM and mobile parameters using EM approach. As a result, our model was able to achieve efficiency without sacrificing safety. Potential future work includes, first, we can use different distributions to define the latent variables. Also, we can use different scenarios and data set to analyze generalizability of our model. That's all I have for today. Thank you for listening.
Good, thank you very much. And thanks for that rapid but extremely clear presentation. Really appreciate it. We'll come back to questions in the panel session. So if you could stop sharing. Hal, are you there?
I am, yep.
Yeah, great. If we could swap over, hopefully you can present yourself. That looks good. I can see you. I'm sure the slides will appear soon.
Yeah. Yep. Can we see that?
Yes. Perfect.
Brilliant. Okay. So I'm Hal Ashton. I'm just finishing my PhD at UCL in the Financial Computing Department. And today I'll be presenting my paper, Defining and Identifying the Legal Culpability of Side Effects Using Causal Graphs. The study of side effect avoidance is a recent research topic in the SafeAI research. It was identified in the paper Concrete Problems as AI Safety by Amodi et al. 2016, and it's one of their top 5 problems in AI safety. The problem is that what constitutes a side effect has been left somewhat vague ever since. In that original paper, it seemed to refer to any caused effect which didn't explicitly appear in the objective function of the AI, and I'll argue a bit later that that is a bit too lax. More recently, this problem's begin to overlap with the related problem of value alignment. Being vague about what constitutes a side effect is a problem because, firstly, with no definition, it's difficult to guarantee everyone is talking about the same thing. And secondly, the act of labeling something as a side effect applies a moral valence to it. People who cause side effects through their actions are generally deemed to be less culpable than those who cause them intentionally. My general objective is just to get us to a state where we all know what we mean when we talk about side effects, both in discussions between engineers and conversations with non-engineers. So as I mentioned, there's been a fair amount of research on the problem of side effect avoidance with the loose definition of side effects. I think that this existing research works on a wider set of harmful effects than just side effects. And that's kind of neat because it covers other stuff as well, but maybe there is an efficiency cost to some of these methods. This literature tends to think about side effects as those effects which a policy causes, but which aren't represented in the agent's utility function. So a few possible techniques in the literature which have been suggested are impact regularization, where a policy is found subject to minimizing the agent's impact on the world with some world entropy measure. Related is an idea of reversibility. So here the agent tries to do its task with a policy ensuring that whatever impact it has on the world can be undone afterwards. And then this has been generalized more recently to the idea of a policy optimization, which also considers a distribution of all possible future tasks. The idea here being that a good policy is one which does not make certain future tasks impossible. And Subramanian surveys the scene and comes up with a taxonomy to classify all these efforts, and these papers are referenced here. You can make an argument that safe AI research should concentrate on avoiding all harmful effects of an algorithmic agent, full stop, whether they're side effects are intended or unintended. Just make sure that no bad things happen. And talking about concepts like culpability, intent, etc., is the domain of AI ethics and not one that safe AI research should pursue. In practice, I think the algorithmic harms will occur despite best efforts, and the Boeing 737 MAX crashes are a case in point. If we step outside the realm of cyber physical systems into the world of non-embodied algorithmic systems, I think harms often become less obvious because, unlike a robot crashing or colliding with something, things tend to continue as before until someone complains. This applies to many financial applications, but also hiring and firing algorithms and recommenders. And in this way, a system can build up regulatory debt, which a company is unaware of, but which may have to pay in the future. So an understanding of side effects might help us understand why something bad happened in the first place. Was it a bug or a feature of the program, or a problem or deficiency the agent's objective or function in the statistical ML approach? And finally, a clear view of side effects is going to help us understand about the culpability of the algorithm's owners in the event of harm, because that's the way that the legal system works. So I've called it unpeeling the side effects onion because the steps to get a working definition of side effects relied on making a few additional definitions. I think generally when we talk about side effects, the most obvious place we encounter them, the term is medicine. And anyone reading the documentation of any medicine will see a long list of possible side effects that it might cause. And medicine, for good reason, is highly regulated, so it makes sense that side effects are defined here quite strictly. The APA defines them as any reactions secondary to the intended therapeutic effect that may occur following administration of a drug or treatment. From this, we can see that side effects are unintended. So as I said earlier, people have an incentive to mislabel harms as side effects because intentional harms traditionally in society are punished more severely and unintentional harms are punished less severely. So of course, now we've just defined one thing with reference to another, namely intent. Defining intent in terms of an algorithm isn't entirely straightforward. However, I don't think it's unreasonable for any algorithmic agent to have a defined purpose recorded before deployment. In the US, the model penal code actually calls intent purpose, which is helpful when talking about culpable mental states, intent being the most culpable one. The definition is given here. So it's a person acts purposefully with respect to a material element of an offence when it is his conscious object to engage in conduct of that nature or to cause such a result. So in sum, for something to be a side effect, it can't be intended. And there's just one final kink in defining side effects in terms of unintended outcomes, and that is the concept of means-end consistency, which is a rationality constraint recognized in law and philosophy. If some intermediate caused outcome is necessary to occur for the intended outcome to occur, then it is also said to be intended. So more memorably, you cannot intend to make an omelette without intending to break eggs. And in terms of mislabeling side effects, this is the easiest pitfall that any algorithmic agent could fall into. Machine learning systems are given objectives and then tasked with policies that fulfill them and not necessarily told what to do in the middle. So if those policies cause harmful effects whose realization is necessary for the policy as a whole to succeed, then they're not side effects. And here I'll just illustrate means-end intent and side effects with a subject that, judging by its occurrence in the literature, is a primary preoccupation of computer scientists, namely the breaking of vases. In this video, you see Pingu, a young penguin, throwing a cushion at their little sister Pinga in a relatable episode of sibling hijinks. Unfortunately, in the process, the pillow hits the vase on the table, knocking it to the ground. We'll now consider under what circumstances vase breakage is a side effect. If at the point of cushion delivery, Pingu knows that hitting the vase is necessary in order to hit Pinga, because say Pinga is hiding behind it, then by the means-end consistency requirement of intent, Pingu must intend to hit the vase with the cushion. This means that hitting the vase with the cushion is not a side effect in this scenario. However, if we consider a similar scenario, the same situation, except Pingu is not behind the vase, but near the vase. Throwing the cushion might hit the vase in the way to hitting Pinga, but it equally might not. So in this situation, vase breakage is not necessary for Pingu to realize his intention of hitting his sister with a cushion. Thus, it can be labeled a side effect. Of course, Pingu is still viewed culpable in the case of vase breakage as a side effect, and the rest of the paper talks about how the law would decide upon their culpability. So in the paper, I frame my definition of side effects using causal influence diagrams, which are causal DAGs with nodes divided between decision outcomes and rewards. I don't have time today to present it thus, but I can loosely explain the process as follows. First, we identify the intended outcomes of a policy or an algorithm. Next, we identify any intermediate outcomes which are necessary for those intended outcomes to realize. These are the egg-breaking variables, to use the omelette analogy again. And in a DAG, these variables will appear on the path between actions and intended outcomes. So the side effects of a policy correspond to the remaining realizations of variables causally dependent on a policy. So these variables, which are descendants of an action node, but they're not the ancestors of an intended node. And side effects might not realize if an intended outcome realizes, which I think corresponds to our common experience of reading the long list of possible side effects on the packet of any medicine that you might take at any time. And equally, side effects might also realize if the intended outcome doesn't happen. The second part of my paper considers the factors which decide culpability for side effects according to common law. That's the system of law which operates in the US and Canada and the UK and India and Australia. As I mentioned, in the US, the model penal code is a code which describes the various levels of culpability, the mental states for caused harmful outcomes. So in deciding culpability, in declining levels of culpability, there's a purpose, knowledge, recklessness, and negligence. Purpose we talked about, it equates to our common understanding of intent. Knowledge concerns the outcome of actions which are known by the agent to almost certainly occur as a result of their conduct. Recklessness considers the case of harms caused which were foreseeable to the agent, but they unreasonably continued anyway. Negligence covers outcomes of actions which were foreseeably likely to cause harm according to some reasonable person, some reasonable bystander. And in the paper, I present a decision tree which allows you to decide what the culpability for some caused or nearly caused harm is.
Oh, it's a short session. We need to draw this to a close, so we've got a few minutes for discussion.
You've got 5 seconds. So this is based on the culpability definitions in the MPC. It uses questions of intent, causality, possibility of harm, both from the agent's perspective and from the perspective of a reasonable person. Thank you very much.
Thanks. So, ladies and gentlemen, we don't have very many times, so maybe only sort of 5 or 6 minutes for questions. I think we're joined by Gabriel, Pedroza, and Peter He, if that's how we pronounce it, from UCL. So, if you wouldn't mind stopping sharing your screen, we'll turn over for comments and questions now.
Sure.
Thanks. Thank you. So, who'd like to go first? Gabriel, any comments or questions for you?
Yes. The first question is about the definition of safety that was provided in the first presentation. I was just wondering whether this definition can be extended to other kind of data or criteria, because there was just, I observed two main characteristics: the deviation of the trajectory and the collision, something like that. I don't know if the presenter can show the slides.
Mm-hmm.
Was that the definition or the slide towards the end, Gabriel?
Yes, exactly.
This one? Yeah, this
Yeah.
one.
So,
And
yes,
that
please
other,
go
yes,
ahead.
please go ahead.
Oh, what were you going to say?
My question is about your, for instance, considering just 2 criteria, collisions and hard brakes. And I was just wondering whether this can be extended to other criteria, which are probably more complex. Like, for instance, you are detecting a person that is crossing, or a cyclist which is approaching to the vehicle, etc. And the second question, I'm surprised at why you obtained just 0, 0, 0 in the hard brakes criteria.
Oh yeah. So
Yeah, likewise. Yeah.
Right. Yeah. So one of the characteristics of the IDM is it's guaranteeing no collision. So yeah, so both the default IDM plus mobile parameter and the two models using parameter estimation, we guaranteed that there is no break. So it's so this criteria is not really meaningful. It's not comparing in a meaningful way among these three models. Yeah, but I was saying the no heartbreaks. So yeah, and the collisions, the accurate definition is we count the collision when the L2 distance to other vehicle is less than some meters. We used 0.5 meters in this work. Yeah, and then this can be extended to the distance to other road users, including pedestrians and others as well.
Okay, thanks. I think there is a question from the audience. Jean?
Yeah. Any other questions? Sorry, because you've shared, if you could unshare again, because I actually can't see the audience right now.
Mm-hmm.
Yes. Can you hear me?
Yes. Yeah, please, Chen.
Yes.
Please, go ahead.
Well, my first question is there any reason for selecting ITM for your approach other than other car following? Because I know there are many other models existing.
Mm-hmm.
And
yes. So, yeah, that was, it was more of a choice that we made for our model. There can be other models that can be applied or used for this modeling. One reason for using IDM for the car following model was that it's more intuitively it's more intuitive, and I'm not really familiar with all the other driver models. Yeah.
Okay. Yep.
Thanks. Thanks, Chen. Because you put a question in the chat. Do you want to put that, and then I was like, if you could stop sharing, that would be really helpful. Thanks.
Yep. So I've got one question. It's how do the collisions compare with real world data? So if I got like whatever population of agents to drive in a real setting, how does 0.0032 actually compare?
Right. Yeah, so that's one of the work that we are currently doing, comparing against the collisions in the real world data. Yeah, and in the scenario that we are using, it's based on a highway scenario where there are not many collisions, but we don't have the number that we can compare for now. It will be one of the extension of this work.
Okay, cool. And I'm just wondering how the agent's state of mind is determined in the culpability framework, because I mean, I can understand how we can find something like what a reasonable person would foresee, but how does that translate into, say, like the current deep reinforcement learning agents that a lot of people are working on? This was at HAL.
For HAL.
Sorry. Yeah.
Can you repeat the last part of your question?
So
this was at HAL.
Oh.
Basically, I think you need to think about intent of the agent and the programmer in unison. Certain models of cognition actually the intent can't exist at all. Mental states don't really exist in model-free models. So you need to think about not only the algorithmic agent, but also the programmer or the owners of that agent. And if you look at law, you might say that then that opens up a responsibility gap, because the programmer might say, "Oh, we've got no idea what our agent is going to do next." But the law has kind of very strict rules about putting your head in the sand as regards to or turning a blind eye on purpose. So I think the response from the law would be, first of all, someone will be held responsible for any harms that are committed, but also by asking that question in terms of mental states, perhaps that's slightly suggestive. If you break down the question in terms of what things are foreseeable, and does the agent have knowledge, then those kind of questions I think are less contentious when we're talking about algorithmic agents rather than mental states. So, and those two questions are really the kind of key drivers for intent. So perhaps we can find intent in algorithmic agents without actually forcing them to kind of programmatically define it themselves, if that answers your question.
Yeah.
Might I briefly follow up, although I'm mindful of the time. I mean, intent is a human attribute, not an algorithmic one. Computers are not moral agents, at least they're not normally held as being so. So I don't even understand how you would assign intent to an algorithm. Is that what you propose to do? Because that's how it sounded to me.
I mean, firstly, your first statement, I don't think is a uniquely human thing. We've shown that it exists in crows, it exists in octopi.
Sure, but it relates to animals, not computers. Yeah.
But the second thing as well is that just because we don't, there is an idea that just because we don't name it as such, something can still exist in the system. So if you look at the kind of fundamental definition of intent, it involves planning ahead, having a plan, committing to that plan, and knowing what the outcome of that plan is. So certain AI agents will do that. Certain AI agents won't do that. So Q learning, for example, has no concept of what state of the world will occur after an action is committed. So a Q learner cannot have intent. However, if I were to deliberately, as the owner of the algorithm, and there will always be an owner of an algorithm who is a moral agent, whether that's a company or a person. If that person deploys an algorithm deliberately, and that design of that algorithm has no, it doesn't plan or say it's a Q learning agent, the question of intent would then fall more directly onto the owner of the algorithm. And then you would kind of use this legal doctrine of is this person deliberately turning a blind eye as to the likely policy or the likely actions of the algorithm. So I think algorithmic intent could potentially exist inside an algorithm, but more generally you want to think about it more as a construct between the programmer or owner of the algorithm and the algorithm itself.
Thanks. Just I think there's a lot of interesting points to debate about that, but I mean, thanks for that very interesting response. So, ladies and gentlemen, I'm aware we're even over the revised schedule, we're a little bit over time. Does anybody have any last question for either of the speakers? If not, I'll say thanks to you both for that, and now we sort of move on to the short poster session. So thanks very much to both of you. I hope you found the feedback and questions useful as well. Thanks.
Thank you.
Okay.
Thanks.